So the how do we do the size tuning is unlike the conventional chemical synthesis routes. Ion radiation provides a direct and controllable method for producing these quantum dots. Under low energy ion radiation, the graphene sheet can progressively fragment into nanoscale sp2 domains, and this allows systematic tuning of graphene size, confinement strength, electronic response, vibrational response, and we'll look at many of these parameters. So GQDs therefore provide an ideal system to study the interplay between the confinement, disorder, and some phonon dynamics. Now coming to the electronic structure of these GQDs, with more than 10 times better electronic conduction properties than silicon, graphene is considered silicon's ideal replacement. This promises to deliver electronic devices much smaller, faster, more flexible, and more efficient than their silicon analogs. However, roadblock for making such devices with graphene is the lack of sizable band gap index electronic energy band structure. So, as we know, the band structure of graphene looks something like this. The valence band and conduction band meet at the pi star band, show a linear relationship between the electronic energy and momentum and meet at the K point. So this is the DFT band structure, and this makes graphene a zero gap material, and aim is to understand and manipulate this 2D material and to make it better suitable for use in electronic devices. So graphene on nanometer scale opens up the band gap, providing interesting optical properties. Some GQDs have been prepared by hydrothermal method also, by organic synthesis, electrochemical techniques. Still, there are several limitations to these methods since GQDs do not always show visible light absorption or prominent UV response unless they are doped, functionalized, or integrated with metal nanoparticles. So outline basically is the formation of GQDs, photo response of these graphene quantum dots, their temperature dependence using some Raman studies, and DFT, phonon calculations, and also the formation of some kind of stone walls defects in these graphene GQDs. So the way the GQDs are made, you start with the single layer graphene, monolayer graphene, and you bombard it with argon ions. Uh, Energies of the ions that have been used are somewhere between 100 and 300 eV, and the fluence is between the fluence is has been kept same, 2.2 10 to the power 14, and then Raman AFM and so on has been done. These are the some AFM images. This is what the single layer monolayer pristine graphene looks. All images are 200 by 200 nanometer. Once you irradiate with the 100 ev argon ions, what you start seeing are some bright spots, and these bright spots are actually the regions where the sp2 has been deformed into the sp3. So it is the in between regions which will give you the where you can find the sp2 structures, and similarly this is at 200 ev and 300 ev. So what we are looking for are the regions where the sp3 has been created, or where the distorted sp2 clusters are there, and where the sp2 clusters still remain. So this La is the size of the correlation length or the undamaged zones, and which will give us the quantum dots. So these are the so one can calculate the correlation length. You need this Trinistra Coing relationship from the Raman, and from one can look at the ID by Ig ratio from the Raman, and lambda is the wavelength of the laser which is being used, and one can also calculate this quantum dots or sp2 domains from AFM where the damage is not there, and one sees that the starting with the single layer graphene, one is can create nano dots or quantum dots between these 9 nanometer or and 3 nanometer, and these mostly get produced around 100 ev argon ion energies. So with the increasing energy, the dot size decreases, and at 300 eV is actually the amorphization, as is shown by the Raman studies. So it's basically the introduction of point defects in graphene with scatter phonons, influencing the frequencies and asymmetries of the Raman allowed excitations. And as the defects get introduced into the lattice, force constants of bonds get modified and can become harder or softer. I will see the Raman in the next slide. The most common defect that are created in graphene during knockout events are the point vacancies caused by the breaking of CC bonds and involve about 7.6 to 7.9 eV. So, and formation of die vacancy in graphene involves about 1 eV more energy. This is the photo response of these graphene quantum dots. So the black one is the pristine one. And if you notice that it is near wavelength independent absorption in pristine, which is as expected to be. And one can also derive this alpha 137 from the fine structure using this absorption coefficient. But after irradiation, so this in the beginning the photo response is up high, somewhere 100, 150, 200. If you see, they are somewhere here, but at 250 it is this one, and 300 is this one. 300, the structure has already amorphized, so this is the amorphous, and these are the interference patterns also suggest that. This 250 is the interesting one. This gives a very nice absorption peak around 540 nanometer in GQDs, and this is suggests the opening of the band gap in the graphene quantum dot. And 70% enhancements in UV photo response after 150 eV or in this range is also seen. This UV response, and all this is in absence of any metallic impurity. It is just the ion radiation which has created the GQDs. So quantum confined nanostructures are achieved by ion radiation, and they present rich and interesting absorption behavior. Then these changes indicate modification of the electronic structure through quantum confinement, defect assisted transitions, edge states, and localized pi electron domains. This is the Raman. So basically the pristine has only the G mode, and as we increase the energies, this D mode appears at some point. This 300 eV is all amorphized. Then this is how the G mode is changing as a function of energy, and as I mentioned that here it is single layer graphene, and here we have seen the presence of quantum dots in all this range, and this is the D. The hexagonal D mode is basically the breathing mode of the hexagons, and initially it is just disturbed, and at some point the bonds break, and then this D mode keeps decreasing. ID by Ig has been used to calculate the quantum dot size, and in this range around 300 eV energy. This is as a function of energy, irradiation energy. So at 300 eV, amorphization is taking place. So this increase in ID by Ig suggests that there is a distortion in the rings, opening up of sp2 rings, and we know that there is a formation of sp3s happening, and distorted sp2 clusters are. This is also XPS has been done. So this also, after analysis, one shows that the ratio of sp3 to sp2 is increasing as the energy is increasing, which is also shown by the ID by Ig ratio of the Raman spectroscopy. And this increase in sp3 content in the SLG is what contributes to the synthesis of these graphene quantum dots. Next, we do the temperature dependent Raman. So temperature dependent Raman spectroscopy provides a direct probe for phonon dynamics in confined system. The Raman G mode is highly sensitive to bond stiffness, sp2 ordering, phonon confinement, and harmonic interactions, and electron phonon coupling. And as in the previous speaker also talked about this decay equation, that this change in the frequency, the G mode frequency, depends on this interaction of phonon-phonon interactions and harmonic phonon couplings, and this can be interactions can be 3 phonon, 4 phonon, or this can also be due to the electron phonon coupling. In pristine graphene, temperature evolution of G mode reflects intrinsic and harmonic phonon decay due to this 3 phonon or 4 phonon processes. Whereas in confined graphene, quantum dots temperature evolution is expected to be strongly modified by finite size effects, enhanced boundary scattering, defect limited phonon transport, and also change in any anharmonic phonon-phonon channels. So this is the G mode position with temperature for various irradiation energies. This is the the blue one is what the pristine looks like, and this is as expected from the reference. Whereas if you see that these are the ones which are quantum dots, these are the increasing decreasing size of quantum dots, and the last one is the amorphized. So this is basically showing an interplay between the size and the defect. Here the defects are increased, so the slope of the curves you can see these are still under uh, publication mode. So increasing irradiation progressively transforms graphene from a coherent phonon system into a confined and defect controlled vibration. So in the case of pristine, that is this blue one, if you see, is basically the phonon decay, and it's mostly intrinsic and harmonic. Whereas between this 100 and 150 eV, which is this these two curves, if you see this and harmonicity is still active, whereas here the defects have already started playing a role. There's a thermal redshift weakens and increased defect scattering, and this is also associated with the lower phonon lifetime, which I have not included in this talk. Uh, but the phonon lifetime increase as a function of temperature, and they increase as the quantum dot size decrease. And at higher irradiation energies, that is around here, highly confined and amorphous like domains have appeared, and T evolution strongly is suppressed and saturates. So basically we are seeing a strong enharmonic phonon dynamics, mixed enharmonic and defect limited behavior, and localized defect dominated vibrations. This is a DFT using the vacancies. So this is a little busy curve. The blue lines are at 0 Kelvin with this vacancy, 0.6% vacancy in the system. And the red is basically the phonon dynamics. Both are phonon dynamics, blue one also and the red one also. So blue one, you see the sharp excitations, whereas the red one is after the phonon dynamics at 0K, and this is at 300K, and this is at 50K, the red one, and this has been done using lamps and a supercell of 20 by 20 by 1. So there are finite size effects, strong phonon scattering by defects, enhanced boundary scattering, defect limited phonon transport, loss of sharp dispersion. This basically the bands are no more sharp and it is all dispersed. Emergence of diffuse spectral wave. Phonons are no longer fully coherent block excitation, and onset of defect limited vibrational dynamics. And very interesting to see is this happening to the ZA mode. This is the flexure bond, which is basically carrying the current, thermodynamics. Then there is also this Stonewall's defects are just basically the 5-7 ring defects of topological defect structure in graphene. and they form due to the rotation of C double bond C. Here, instead of you see two, instead of four hexagons, there are 5 7 rings, and these are expected during rapid quenching from high temperature or when graphene is under irradiation, and they can allow opening of the electronic energy band. So these SW introduce only local disturbance with no long range effects, and their numbers are small. So they are difficult to experimentally study them. DFT studies on graphene have shown phonons and Raman excitation profiles for topological defects, these SW defects. And first principle analysis have also shown that the frequencies of GD bands get affected by concentration of SW defects. And detection of these defects by a Raman or vibrational density state can provide easier determination. These are some studies in literature where TM has seen the SW defects, and this is the DFT of the same thing. And although such defects are prevalent in ion irradiated graphene, these defects are difficult to observe in Raman experiments. And the reason of weak Raman intensity is because their several signatures overlap with other prominent Raman bands, making their detection harder. And the formation energy of this mono vacancy is 7.5, di vacancy is 8 eV, and SW defect is lowest. Actually, it's only 5 eV, so it's very easy to make these kind of defects. And these are the DFT studies which basically show that at the presence of SW defects, what all changes happen in the G band and the D band. So the local vibration modes associated with the stone wall defect in graphene, when there is something like 2% concentration of defects. G band displacement along unrotated CC bond will give frequency of 1556, and displacement of perpendicular unrotated CC frequency will give this. So these are the things one can check what is happening to the G band, and the D band with SW defect will have this frequency. But most importantly is the appearance of this SW defect mode at this. But it's difficult to visualize when the various bands are overlapping. So stretching of stiff rotated CC band at the center of the defect, and there are also suggestion of vibrational modes about at 2142 for these kind of modes. And this is further to suggest what modes changes will take. So formation of short and stiff CC bond at the center of SW defect leads to softening of G band and hardening of D band. And the rotated CC bond at the center of SW defect will be little shorter. So one can check all these things, and what we have done in the Raman, what we have seen that the pristine doesn't show this mode, of course, but as we irradiate at around this 2000, a little more than 2000 wave number, you see these modes, and these are due to the stone wall defect, or it can also be non-hexagonal rings which are leading to these kind of defects. One can enlarge it and see. And again, the energy is between 100 and 300 eV. Single layer graphene and multi-layer graphene both have been studied here. Pristine, of course, do not show, and it is difficult to see in MLG. If you see, MLG is much lower in intensity than SLG, and that is due to the linkage and van der Waals interactions which are happening. However, for later stages, MLG survives whereas SLG goes up. So in summary, low energy argon ion irradiation provides a controllable GQDs, shows strong modification of the optical response including enhanced UV absorption and new optical transitions. Temperature dependent Raman measurements show that pristine and weakly irradiated graphene retain a strong and harmonic thermal softening of the G mode. At higher irradiation energies, the crossover from nanocrystalline to amorphous like graphene results in defect dominated vibrational behavior. DFT phonon calculations reveal phonon softening, line width broadening, and short perturbation of flexural phonons. This is that ZO mode which is showing immense modifications once the vacancy is put in. Under vacancy induced disorder, this work has been done at is being done at various vacancy concentrations and temperatures. And ion irradiation of SLG and bilayer graphene at low energy shows signatures of this is stone wall defect. So these are the collaborators, these are my students, and this work has been done in collaboration with the University of Nebraska, and DFT work is being carried out at Pondicherry University. And of course, acknowledgements to SCRB, which is now ANRF, and also IOP and IUAC in these studies. Thank you.
Thank you very much. So the session is open for the question answers. So are there any questions?
Late in the evening, I guess.
Students. So I have a question. So when you have this quantum dot in graphene, how many like are there in the dots? Like how many dots is created? Is one dot or like just a several array of
No,
dots?
there will be several. It's
Okay.
a single layer graphene.
Okay.
So the density is, so the ion radiation density is of the order of 10 to the power 14. And the density of GQDs that we expect is of the order of 10 to the power 4, maybe, in that SLG, which is about 1 centimeter by 1 centimeter. Yeah.
And do they interact with each other?
That is not clear. That I think that information we are getting from the temperature dependent. That there is a kind of interaction, but that is still is being evaluated.
Okay.
So when you bombard the graphene sheets with the argon ions, so is there any bond pairing you see?
Is there any?
Bond pairing, the CC bond?
Yes, CC bonds are breaking.
Breaking.
And the vacancies are getting created. That's precisely the reason why the sp2 is getting converted to sp3 and leading to the regions. So there are sp2 regions which are separated by sp3 regions, and sp2 is the graphene quantum dot, and sp3 becomes the defect.
So in your experiment, is it possible to account for the elastic limit of the bonds? Is it possible that how much I can bombard and I am still in the elastic limit of the bonds? Is it possible to account such information?
I think one can get it, but probably from the DFT, because we are doing DFT that can probably supply this information using it.
And then we can then the experiment can be designed.
Yes.
Okay.
This lamps is a very powerful technique, because as a function of temperature it can give us all the
Yes.
bond strengths and
It happens instantaneously, I guess.
yes.
Hello, ma'am. Nice talk. Ma'am, I had one question that when we think about this quantum dots from a application point of view, then how do you suggest like for the biosensing or anything? Is it like how will we make the film for that? Is it a like deposition or is it these solution processable?
See, right now many people are using RGO, which is a simpler way of using. But if you want to use actual graphene quantum dots, like in this study has been done, it is not very difficult to prepare, because it's a single step process. We just took commercial SLG, or one can make single layer graphene or multi-layer graphene, and you bombard it with argon ions, right? And you are getting, depending on the energy, just the energy and the fluence, you are getting the graphene quantum dot. So it depends what is your purpose of the study, and what is your ambition, and what is you are looking for motivation, and so it will depend. But as I said, right now the easy route is functionalized graphene or reduced graphene oxide, which people are looking for. So if you are doing biosensing work, both the things are possible. And
And all the Raman like experiments that you have done, like in which state did you the temperature dependent Raman and all? Was it all like solid state thing or?
yes, so solid state thing means,
I mean, like
yeah, we have a closed cycle refrigerator, CCR type Raman head,
so it's
in
an
which it can.
integrated system. Okay.
So are there any more questions?
I'm Aishma. So I have a small question that in graphene it is said that it forms a Dirac cone for matrix polynomial. So what inflection actually causes this cone kind of band structure?
Okay, that is a question I think we can answer after this session. Okay. It's basically it is meeting at the K point. Both the valence band and the conduction band are meeting, and that's why it is a there's no band gap. Yeah. It's a triangular thing which is meeting at a point at the K point. Yeah, that's what I'm saying. We can talk. That's a detailed answer, and we can do it after this.
Okay, so thank you very much, ma'am, for the talk. Let's thank the speaker again.